Can you hear me? Yeah, good in the back. Cool. All right.
Please, thanks.
Yeah, let's go. So it's 33. Okay. Alrighty. Hi, everybody. So yeah, I think the title is pretty self-explanatory. Gonna talk about string theory. Um, but I'm going to try to take a non-conventional approach, I would say, compared to like most textbooks and lecture notes you'll find around. Um, Mostly because I don't have that much time. Actually, it's kind of a weird range of time, right? Because it's way too long for just a seminar, but it's not long enough for an actual full course. So it's kind of in between. So I'm going to try my best to fit what I want to say in this time period. And to that end, I really would like you guys to interact, ask questions, and or tell me if I'm going too slow, too fast, too technical, too trivial, anything, right? So, don't be shy. All right. So first of all, I want to thank the previous lecturers for introducing all the right conventions about everything and for introducing a bunch of topics that will be extremely useful for me to reference, both either, explicitly or implicitly, depends. All right. So what did I write here? Well, yeah, I mean, here's a sketch of plan. So part one, actually part zero is done. Uh, I'm not gonna start, with the conventional approach of just saying, okay, let's talk about strings, right? I mean, there's not really much point in that, in my opinion, when it comes to the theme of this school and subsequent workshop. The theme is quantum gravity, broadly speaking, which means we should begin with some common ground on what quantum gravity should be, right? And the common ground is effective field theory, just like Anna, taught us in her lectures. So that's where I'll start from. I'm gonna try to squeeze every bit of information we can from effective field theory. From now on, I'm going to try to just say EFT to save time, right? But implicitly, gravity is always there. And in particular, it's gonna be an EFT with gravity, dominated by GR, right? You could start your effective action with like R squared or whatever, but we want, rocks to attract with the 1 over R squared force. So we really want GR plus corrections, right? Not just the corrections. So this is what I mean when I say EFT, right? So I want to start there and talk about general features. So, some relevant scales and some aspects that are unique to gravity, such as some features of black holes, right? And eventually, I'm going to give you some motivations to indicate that perhaps something that looks like string theory is a worthwhile approach to take, right? So that's the idea. Cool. So, part two, and this is where ideally we should get by today, right? Is just the actual construction of the theory. Now, of course, I could not possibly cover all that is known about string theory in not even 60 hours, let alone 6. So I'm going to try to focus on one little corner. Like if this is the whole theory that we know of, this would be the kind of thing I'm going to talk about today. But in my opinion, it's a really relevant corner for multiple reasons. In particular, because it embodies most, if not, well, okay, let's say most of the relevant aspects for quantum gravity, right? And it's one of the most well understood corners of the theory, right? Where we have like very good definitions about things, and we can actually speak quite sharply about many quantities and so on. And what is this corner? Well, you may not be surprised to hear that in this corner, interactions are weak, right? So we want, some weakly coupled strings. And actually, this is kind of almost the only context in which it makes sense to call this string theory proper, in the sense that much like it makes sense to talk about particles in relativistic quantum field theory only when the interactions are weak, otherwise they're just quantum fields doing what they do. Similarly, strings are like the particles of QFT. They are excitations that interact weakly, and as you crank up your couplings, they start meshing with the background, right? In something that it gets way more messy, and it's not clear, what are the fundamental degrees of freedom and what is the rest becomes blurry, right? This is completely normal. It's what happens in pretty much all of physics. Right? So I'm gonna talk about weakly coupled strings. Now, this already is a lot of stuff, so I'm gonna restrict further. I want my strings to be only closed oriented, to be more precise. Because strings can be closed and they can be open, they can be oriented, and they can be unoriented, right? And it turns out you can keep just closed strings, at least in the weakly coupled regime. Turns out there are always open strings in the non-perturbative sector in some way. Actually, a cool paper about this came out this morning. I digress. So you can only fixate on closed strings if you want in the perturbative regime. Whereas if you look at open strings, then you're forced to look at closed strings. Like this is the sector that you're forced to look at. Amusingly enough, it is also the sector that produces gravity. So we're forced to have gravity. And we're also forced to have some type of gravity whose leading low energy description is this. So basically, in string theory, this definition of quantum gravity is completely unavoidable. It's forced on us. We don't like put it by hand or anything. It's completely unavoidable. Cool. Oh, by the way, if you have any questions or comments or anything, please interrupt me at any time. You don't have to wait like for specific times. I'll try to keep track of the 45-minute unofficial break that we have been doing apparently, but you don't have to wait for that. Right? Yes. Is this clear for now? I mean, I can write the rest bigger. At least I'll try. Okay, cool. Good. So this is what I want to do today, right? I want to get to the theory and build it together. And then tomorrow, I would like to, look at some physical implications, namely what happens at low energies, namely this, like how do we actually get to an EFT of gravity? And what happens in the high energy regime, right? What happens when you smash strings super hard, right? And the cool thing, I mean, I will repeat this over and over probably, but the cool thing about this is that the high energy, extremely high energy regime is somehow universal. It doesn't really depend on the details of like the vacuum state that you start from. Because UV means tiny scales, which means that if your space-time is doing weird stuff with slow variations over long distance scales, the microscopic physics will not care about it, right? And this is reflected in the actual calculations that I'll try to present. Whereas in the IR, we will learn that much like any theory of gravity, there is a bunch of possible vacuum configurations whose excitations, low energy excitations around them give rise to EFTs, right? And we will learn about the landscape of these EFTs, the set of the possible low energy laws of physics or universes or whatever you want to call them, you can get from the theory. And this is not writing bigger, so let me actually write bigger. Right? So we are led to the concept of the string landscape.
There's a question in the chat.
Yes.
What would be a vacuum configuration? Is it a preferred state as in QFT or something else?
This is a very, very good question, which is actually answered by an excessively long footnote in my notes. So the answer is complicated. So the thing is, in a non-gravitational quantum system, a vacuum state is just a ground state of the Hamiltonian. Simple as that. In a gravitational system, it's more complicated because it's not obvious what the notion of Hamiltonian means. It's not obvious that space-time is dynamical. It need not be globally hyperbolic. It need not be foliable by space like Cauchy surfaces, right? So what does energy mean? What does vacuum mean? Well, turns out even just at the level of classical GR, there is a way to define energy, right? In certain contexts. For example, if spacetime is asymptotically flat, or if it's asymptotically anti de Sitter, there are notions of energy that sort of are supported on the boundary of space, right? So, for example, the ADM mass, the Arnold-Witt-Deser-Misner mass, or Komar mass are examples of these kinds of things. And they are more or less, geometric intrinsic generalizations of the nether charge from, coming from the stress energy tensor. Now, this is classically. Quantum mechanically, this sort of asymptotic boundary structure at infinity, for example, asymptotically flat or asymptotically anti de Sitter, is still fixed because, it takes infinite action to fluctuate the boundary at infinity. Like in the middle space-time, like if this is the boundary at infinity, in the middle space-time will do all kinds of things, but this boundary is fixed. And because this is a quantum mechanical system, we can say that actually it is super selected because no matrix element of any observables will ever mix to different asymptotic boundary conditions, right? Why is this relevant for the question? Because given such asymptotic boundary condition, you can usually use that notion of energy or the quantum mechanical counterpart thereof to define a bona fide vacuum in that sector. So you gotta fix the asymptotics first, and then you can ask what is a vacuum, right? So this is what a vacuum configuration should be at the exact complete non-perturbative level. We will give a precise definition of a perturbative vacuum, or if you will, a classical vacuum, right? Which is, a weaker notion, because a classical vacuum can be an exact vacuum, or it could be merely metastable, right? It could be subject to tunneling to something else. Right? So at the level of perturbation theory, it's impossible to detect whether a classical vacuum is unstable or completely exactly stable. I hope this answers the question, but I will give a precise definition at some point, likely toward the end of today's lecture, of what a classical string vacuum is. Yes. Well, so it's any energy scale that is parametrically smaller than the cutoff of the effective field theory. Now, what is the actual cutoff of the effective field theory will depend on the precise, setting that you are in, right? So, for example, if there are no other, like what I'm trying to say is that all the data about these EFTs, cutoff included, is completely fixed by the choice of vacuum configuration, right? So for more or less generic configurations, and I will be more specific later, the cutoff of the effective field theory will be the scale corresponding to the tension of the strings, right? So these EFTs will have some cutoff, okay? And this cutoff, quite often in weakly coupled string theory, is what I'm going to call the string scale, MS, right? Which is defined as just the square root of the string tension I will introduce soon enough, right? So it need not be this. It could be something smaller than this. But roughly generically, in weakly interacting string theory, this is what the cutoff will be, and this is what low energy means. It means that you're looking at observables whose typical support in invariant energies, like Mandelstam variables, for example, is much less than the scale. Does that make sense? Cool. All right. What do you mean by degrees of freedom? Do you mean the species of quantum fields, distinct quantum fields? Well, it depends. It changes depending on the vacuum configuration. But it seems to be always a number of order one. By order one, I mean that there is no family of EFTs, a sequence of EFTs where the number of degrees of freedom diverges as you go. Right? This has never happened. There is no foolproof in full generality, as far as I know. I'm actually kind of working on it. But in sub cases, one can actually show that this is the case. Yes. Right, we're getting to the advanced stuff really fast, actually. All right, all right. So yeah, so this is the IR stuff. Now we will learn about.
Effectively, the lambda is the cutoff.
Yes.
You don't know, it's not a physical scale. In string theory, MS is a physical scale.
Yes, I mean it needs to any UV complete theory. If it has an EFT regime, the cutoff of this EFT description will be predicted by some physical scale, of course. Like the UV completion needs to predict everything about the EFT. Cutoff, Wilson coefficients, everything. So yeah, so this is completely expected, right?
Yeah. MS is something that is like H bar.
Well, H bar is one.
Okay, it's not like the cutoff of the effective field.
But right. So my point is, from the perspective of the EFT, this is the scale of new physics, and the EFT is agnostic about what the new physics is. From this point of view, what one could call the top-down point of view, we know what the scale is and what the new physics is. Simple as that. Okay, very good, very good. So we will learn about this, sort of poetic name for the set of EFTs that string theory produces. I'm gonna give you some generalities before actually delving into the details, because I know you want to know the punchline. And also, I will try to talk about some general features. Some general features. Emphasis on general in the sense that they hold for all these EFTs, right? Across the landscape, or at least in this tiny little corner of the landscape, right? The ones that maybe we can show using weakly coupled, perturbation theory. Right. Okay, so this is part 3. And part 4 will be like the juicy quantum gravity stuff, right? The actual genuine quantum gravitational features of the high energy physics that you want to know about. And again, as I was writing, these features are largely universal, as you would expect. Like, for example, in usual relativistic QFT, if you scatter massive particles super hard, the fact that they have a mass barely matters. Right? It's a similar thing. Or if you do it in curved space, like in a curved asymptotically flat space, the details of the geometry will not matter as long as the typical variation scale is parametrically smaller than the energy at which you smash them. Right? So this is completely expected and also quite convenient. But then there is also some less expected features that come from the fact that this is not just a UV complete theory, it's a UV complete theory of gravity. Namely, the UV effects are inextricably mixed with the infrared effects. So this is a super cool feature of gravity that we'll review starting, shortly. And this is one of the deepest things about quantum gravity that really make it, different relative to the other stuff we see. Yes.
They ask if you will discuss still.
I won't. Sorry. But I mean, there's plenty of okay. Yeah, this is a good time to mention. So I have excessively long notes that we sent you guys this morning, so you can check them out. And in there are a bunch of references, not just like a bibliography for the various little comments and way too many footnotes, but also like a list of actual textbooks and lecture notes and even some seminars with the YouTube links, where you can find more material, including some string cosmology. All right. So this is the plan. This is the plan with a little pretty drawing right there. Any further questions? Okay, if not, there is. Is it common to set them as a general approach? Right. So it's not that it's whether it's common or not to set the cutoff. Sorry, you're right. So is it common to set this UV cutoff to be the string scale? Because as the person who was asking the question rightfully mentioning, sometimes it's something else, which is something I was mentioning earlier, right? It's not always that. It is often that in the context of weakly coupled string theory. And it's not about whether we set it to be this or that. It's fixed, right? Like it's determined by the situation, by what sector of the theory we are in. So we don't get to choose. Like this is actually kind of a theme in string theory. We don't get to choose. Like the theory does it for us. The only thing we get to choose, similarly to any quantum system, is the state where we're in. That's all. So sometimes, in fact, as it's mentioned, as is mentioned in the question, sometimes this cutoff will be the scale, the length scale of some extra dimensions, for example. Like if there are extra dimensions with some typical length scale, called the Kaluza-Klein scale in this question, it's called like that, then that will be the cutoff of the effective field theory, as you would expect, right? Okay. So yes, that can sometimes happen, but it depends who wins between the two scales. The lowest, so the cutoff is the lowest scale at which new physics shows up. Yeah, that's simple as that. Cool. All right. I hope I answered exhaustively. Right. So speaking of UV cutoffs, let's begin with effective field theory, right? So maybe I can put like some GR in brackets, not just to emphasize that it's a gravitational EFT with a GR leading order, control, but also because it's funny to say greft. I really find it very funny. It's even funnier if you put standard model in there; it becomes grsmeft. Quite a mouthful. Okay, so what's the structure of this thing? So this is supposed to be the common ground, right, where everybody should be more or less on the same page, right? And the same page should be that there is some effective action, right, in the Wilsonian kind of thinking, even though we will see that it doesn't really work for everything about it. So what is an effective action in this framework? Well, there's the leading piece, and then there's higher derivative corrections weighed by the scalars, right? But it's not so simple. So first of all, the series, it's not like it's gonna converge in any meaningful sense. It's at best, it's going to be an asymptotic series, probably divergent. So I'm going to put this little sign over here. Maybe I can also give an explanation of the notation I'm going to use, the asymptotic notation I'm going to use. But how does this thing look like? Well, it's a theory of gravity, right? So let's say we have some d-dimensional spacetime. I'm using the obviously correct signature here, the mostly plus, right, as everybody else did, which I'm very happy about. And what do we have? Well, at low energies, what dominates is everything except for gravity, right? So at low energies, weakly coupled quantum fields can be of a handful of types compatible with, local relativistic invariants and so on. You can have scalar fields, you can have vector fields, you can have fermions, and that's about it, right? And then you can have the graviton, and then you can have a Rarita-Schwinger field, a helicity 3/2 field. But if you have both, you have supergravity, actually. So let's say we have some sector. Well, actually, let me say stuff. Some sector that contains everything except for gravity, right? And then we have our beloved gravitational sector, which was explained beautifully by the previous lectures. So let's say we have our Planck scale to the d-2, right? And we have our Einstein-Hilbert term. We can have a cosmological constant, but the cosmological constant, if you think about it, is just a special case for a potential for scalar fields. So I'm just gonna shove it in here. So this is the gravitational piece. And then we have the corrections, right? So what kind of corrections can we have? Well, as was explained in previous lectures, it's generally all the possible gauge invariant and scalar operators that exist in depending on the field content and so on. And they can be essentially of two origins, right? They will involve everything, all the curvatures, all the the field strengths of gauge fields, scalar fields, all of that. But I want to emphasize here, this is very important. They come from two different things. So let's say you have some massive quantum fields, right? I don't know, some new species of quark, whatever, very heavy, and you integrate it out in the RG flow, right? What happens is that it will contribute higher derivative corrections, including gravitational ones, but they are of field theoretic origin. This has nothing to do with quantum gravity, right? Just because you have higher derivative corrections in the gravitational curvatures doesn't mean it's a quantum gravity effect, right? It comes from just integrating out some normal garden variety quantum field. So it ends here. So this thing will contain, let's say, some asymptotic series involving some operators that contain the various fields, right? Some scalars, some vectors, whatever, some derivatives. So this is a derivative, right? So it could be some covariant, gauge covariant, gravitationally covariant derivative, weighed by our cutoff scale. Well, no, actually, weighed by some cutoff. Let me call it maybe in a different way from that one. Let me call it lambda stuff because it refers to this sector here. This is the non-gravitational cutoff, so to speak. An example of which being the Kaluza-Klein scale that was mentioned on Zoom, like the scale of extra dimensions, has nothing to do with quantum gravity. So this will be something, if this has mass dimension k, this will be k and then minus d, right? To make this a dimension d thing that makes things work. So this is the kind of thing that you would expect here, but we don't care about it. This is not a quantum gravitational effect, right? What we care about is the quantum gravitational effects, the ones that know about the Planck scale, right? And this will be, again, a bunch of things with some operators. I mean, not these ones. These will be different, of different origin, so to speak. Will contain, of course, Riemann curvatures, all of that, derivatives, and so on, right? This is a schematic structure. It doesn't really matter for what we're going to say. And then there will be some cutoff, which now it can be a different cutoff relative to this one. And there are explicit examples of this. We understand this decently well by now. And this is what I'm going to call lambda UV. Right? So this is the structure of this gravitational effective field theory that I'm going to start with. This should be the common ground for all of our discussions, right? And I'm making a point of distinguishing between these two cutoffs because it's important, right? So, for example, if you have extra dimensions and they are much bigger than the Planck scale, these two scales are very different. Okie dokie. So, any questions about this structure? Okay, good. So, of course, these guys will be weighed by some Wilson coefficients, right? And these Wilson coefficients, of course, can depend on scalar fields. For example, if you can shift the dependence of scalar fields in the Wilson coefficients if you like. Yes. No. Right. So this is different. Yes, this is different. Yeah. This is gonna be like k minus 2, right? Yeah. That's right. And this is actually another diagnostic of why this turns out to be different from that. Yeah, that's right. Thank you. Cool. You absolutely can.
I would have only one scale, neatly.
Yes, but the fact that these scales can be parametrically separated in some limits, some situations, will show up in the fact that these coefficients relative to these ones could be very big or very large or very small. So there will be a hierarchy. So I'm saying that this is the expression, the way of writing this thing, whereby according to, for instance, the non-hierarchic bounds that were shown to us by Anna, for example, but more broadly speaking, we expect these guys to be order 1 in whatever limit we take. So actually this may be a good moment to explain some asymptotic notation I'm going to use every now and then. So there are a bunch of symbols that I'm going to use, right? Symbols you may have seen in the past, but which for me mean very specific things, right? So stuff like this or this. So this is, I may have written down some other symbols. Actually, no, not really. So these are symbols that apply whenever there's some limit in whatever parameter goes to whatever value. Okay, so this is always implicit because, for example, in EFT, there is a limit involved. The limit being we are implicitly going to eventually compute some observable supported in a region of energy scales, invariant energies, Mandelstam variables, whatever, which, divided by the cutoff is small. So there's the limit there. Or for example, the weakly coupled limit in string theory will be a limit in which some dimensionless coupling goes to 0. So there's always a limit involved, right? And whenever there is a limit involved, you can compare two quantities which depend on whatever limit you're taking. And you can say that whatever quantity you're looking at, always dimensionless quantities, the only physically meaningful ones, you can say that the quantity is order 1 if it remains finite in the limit, finite and doesn't diverge. You can say that two quantities are asymptotic to each other if the ratio goes to 1, or more generally, if it goes to an order 1 constant. And much less means that the ratio goes to 0, like something is much less than the other thing. So this is the asymptotic notation. So this is not asymptotic notation, but I'm gonna use it every now and then. Proportional more precisely means that the ratio is a constant, like something that doesn't depend on any parameters that scale. That's what proportional means to me. And finally, this is what I'm going to use when I'm talking about like topology and worldsheets and, more fancy schmancy things like that. This means homeomorphic, diffeomorphic, isomorphic in whatever sense, but this will apply to like not numerical quantities, but like surfaces and manifolds and stuff like that. Yeah. So this is kind of the notation I'm gonna use. Cool. So this is the general structure of the EFT. Now, what can we do with this? Well, turns out we can do a lot with very little data when the space-time dimension is at least 4, right? Or more precisely, when the number of extended dimensions, right, the ones we care about, the ones that go to infinity, like in that picture, is at least 4. Reason being, below 4, there are no gravitons. And gravitons are sort of the perturbative manifestation of like basically everything we care about in quantum gravity, everything that makes it insidious but also rich of new concepts, right? Like in 3D, it's just a topological theory. In 2D, it's not. I mean, it's just stupid. I mean, it's not stupid when you couple it to matter. Not particularly insightful for what we care about, though. So I'm gonna stick with that. In this case, we can say a bunch of very interesting things, right? This is what I care about. Also, you may happen to notice that the number of dimensions large dimensions that we see is 4. So that's pretty useful to consider this case. Okay. Good. So now, what kind of considerations can we make? Well, let's talk about the scale. Again, this is the scale of new physics. This is the scale of new gravitational physics. This is what we care about, at least what I care about. So this is the MVP. Now, you may happen to think that just like, generally, parametrically, this is true. Parametrically meaning that there can be an order 1 thing here. Oh, sorry, I didn't explain this. This means that, for example, A is this than B means the opposite of this. It's not much smaller. Like it's kind of at least at most as big, but it cannot be too much bigger. No, this is what it means. The logical negation. Yes. So when I talk about equality of scales, scales are not numbers. Scales are sort of defined up to an order 1 number in front that means nothing physically. So this equality means this is an equality of scales, not of numbers. So you may happen to think that this is true. And this is in fact the case with probability 100% in the sense that if you throw a dart in the space of EFTs, you will land somewhere here. So almost all EFTs have Planckian cutoff, but not all of them, right? There's a measure 0 subset in some sense that I could clarify with a concrete example, where this is not true. In fact, weakly coupled string theory doesn't have this. It has some other scale, right? This comes in handy now. So there's some limit we're taking, for example, weakly coupled limit, in which this happens, right? And this is actually what I define as my quantum gravity theory being weakly coupled, right? Why is that? So this means my quantum gravity theory is weakly coupled. Why? Well, because think about it, do some low energy scattering, for example, of gravitons or whatnot. What you'll find is that the effective dimensionless couplings, the ones that were defined, for example, in the previous lecture, that govern graviton scattering at low energies, is going to be of the form some invariant energy, for example, the center of mass energy or some process, over m Planck squared. Right? And you can have powers of this. So this is sort of the effective quantity that tells you if the scattering is weakly coupled or not. This means that much less than Planck, gravitons are weakly coupled, which means that an EFT of gravity is always weakly coupled in the gravitational sector. Then you can have QCD, which is insane, but it's another story. The gravitational sector is weakly coupled at low energies. Right? Now, what happens at high energies? Well, this within the regime of the EFT, by definition, in the gravitational sector, you cannot go above this. Right? So, and so if you see, if this is much smaller than this, and this is, positive, of course, this is gonna be small. But now it's not a statement about the effective field theory being weakly coupled for gravitons. It's a statement about the whole regime of validity of the EFT, right? So you see, if the EFT is valid, let's say in S or square root of S, up to here, right? And all here couplings are, weakly coupled, then not only the EFT is weakly coupled, the EFT lives here, right? This is where the EFT lives. But, it will stay even beyond the EFT weakly coupled, right? You see what I'm trying to say? There will be some other strong coupling scale at some point. Does this make sense? So what I'm saying is, yes. No, all the way to some other scale, which is at most the Planck scale, yes. So by Planck, you reach strong coupling regime. Right, yes. So indeed, what we're saying here is that what is always true by definition is that the UV cutoff is parametrically at most this strong coupling scale, which is at most Planck. Right? This is what we're saying. Now, in EFT, we don't know this, nor this, but in a UV completion, we can in principle compute them, and we shall, right? In these cases. Right. So this is the cool thing about this kind of limit. If this is true, then the quantum gravity theory is weakly coupled, meaning that there is some strong coupling scale parametrically above, well after you need the new physics. So the new physics will still be weakly coupled. That's the point. And this is what string theory does, actually. So in weakly coupled string theory, this happens. So this is what I call weakly coupled quantum gravity. Okay. Now this is important for various reasons. No, so it cannot be parametrically above. This, I would say.
Inconsistent a posteriori per checking or
So in the sense that it never happens, and yeah, that happens. Like we will see explicitly that in this weakly coupled corner, the string scale will be either this or a bit higher. But in the context we'll talk about, it's the UV cutoff, and then this will be some other scale, and then Planck. Right? At least we can estimate what this is. Cool. All right. Thank you for all the questions. It's very helpful to get the feedback. So I by the end of the next 47-ish minutes, I want to get to motivate strings and introduce them briefly, which is I think we're on a good pace for. So good. All right. So this is a very interesting limit, right? So I could just tell you, hey, I'm gonna consider weakly coupled string theory. This is true. So let's take this as a starting point. I could just do that and it would be enough for our purposes. But I can actually tell you something, like a couple things more. So first of all, there's some recent papers there are references in the lecture notes that make an interesting observation. This is kind of one of those observations that you look at it and you're like, why didn't anybody do it before, right? And maybe they did, and maybe I missed it. But there is an observation that this thing, this condition, weakly coupled condition, may be actually necessary to have a good effective field theory in 4D, precisely 4. Now, I'm not sure about this, but I want to mention it as a a little interesting thing. The point is, you see, a priori, you don't need this to have a good EFT. A good EFT only needs that this be small, the physical energy that you probe be smaller relative to. Well, actually, what the EFT needs is this, right? This is what the EFT needs. This is the regime of validity. So you don't need weak couple. These guys could be equal, right? But generically, they will be, right? If you pick a random EFT, they will be. And this is the regime of validity. So do not confuse the validity of the EFT, the low energy description, with the weak coupling description. These are a priori different things. It just so happens to be that gravitons are weakly coupled in the regime of validity of the EFT. Now, it could be that by the time you reach the cutoff, if these are equal, the gravitons become strongly coupled. Could be, right? This is the case in asymptotic safety, for instance, by definition, actually. Good. So you don't need this. But in 4 dimensions, there's something cool you can say. There are some non-perturbative semi-classical effects driven by gravitational instantons. So maybe some of you have heard about instantons. There are some special instantons. So in D equals 4, there exists some gravitational instantons, which are essentially a tool to estimate leading non-perturbative effects whose perturbative contribution is 0. So the first thing you see is the instanton, right? And these are usually weighed by something like e to the minus something big, right? Something big, for example, is what Benjamin wrote in the beginning of his lectures, like e to the minus 1 over g squared, right? These are like Young-Mills instantons, for example. In the case of these gravitational instantons, what happens is that this contribution is led by not the Einstein-Hilbert term, by one of the first higher derivative terms. So this term just cancels out. These are called Eguchi-Hanson instantons, if you want to look them up. But again, it's in the notes. In particular, this thing will be essentially some Wilson coefficient. Maybe I should write it bigger. Wilson coefficient for the Gauss-Bonnet term, right, which in 4D is topological, times the Gauss-Bonnet action, which is like the Euler character of the compactified space-time, which happens to be like 2, and the action is like 1 if you normalize it properly. But the point is that you get something like this. Now, generically, Wilson coefficients, as you said before, if you normalize them in order to be order 1, they will carry another contribution, right? So the Gauss-Bonnet term has dimension 4, right? So you get something like m Planck squared over lambda uv squared, which means that if you want this guy to be suppressed, it implies that lambda uv be much smaller than Planck, right? That's cute. So either you somehow are able to tune this coefficient to be outside of the hierarchy, or for the quantum gravity, so like the validity of the EFT, the parametric validity of the EFT requires weak coupling in the sense. Now, this is an argument about parametrics, asymptotics. Like if you don't have this, like this thing could be like 10 to the 9 or whatever. And e to the 10 to the minus 10 to the 9 is ridiculously small for experimental purposes. But theoretically speaking, it's not a parametrically small thing. It's e to the minus 10 to the 9 in asymptotics language is order 1, right? So it's a parametric statement. It could be false in our universe, and we could still do all our experiments with beautiful accuracy. But it's an interesting thought because it implies something about parametric control. Could be that we don't have parametric control in a realistic theory. Who knows? But anyway, this is a further motivation, which curiously works in 4D, for this. And I'm emphasizing 4D, first of all, because this argument only works in 4D, And I mean, you could, if you take a higher dimensional theory, you can reduce to 4. And also because we have explicit counterexamples in higher dimensions, right? Theories in higher dimensions where this is true, and they are completely consistent within the framework of string theory, broadly speaking, right? So this is an interesting thing, that it could be that not only this is a convenient limit to take, it may be necessary if we want a 4-dimensional, parametrically well-controlled EFT. Cool. I think it's pretty interesting. Good. So I think I've sufficiently motivated, that we would like to look at weakly coupled quantum gravity, right? And again, weakly coupled strings are an example. Okay? So this is what we're gonna do: weakly coupled closed strings. Okay, very good. So maybe another thing I could say. I'm not sure if I have enough time actually. Maybe I'll mention it very quickly. So, okay, we're gonna look at this weakly coupled quantum gravity, right? So please nod your heads to make sure, like, tell me if you're understanding or, okay, thanks. So we have this lack of hierarchy, right? There are no, these are negations of hierarchies. We have these bounds by definition, right? Now, can we say something more? Right? Can we actually estimate these guys somehow? Maybe not estimate, maybe give some upper bounds or something, right? For sure, we know some upper bound, but this is kind of lame. I mean, the Planck scale is way up there. It's ridiculous, right? If everything was Planckian, if all the new physics was Planckian, it would be kind of hopeless to actually test. Well, let's say directly test quantum gravitational effects. They could leave some indirect signature, right? I don't know, inflation, something like that. But that opens up a whole other can of worms. So I'm gonna be concerned with direct tests. So can we say something about that? Turns out we can. So let's see. Maybe I can go to another Blackboard. Okay, so weakly coupled quantum gravity. Right? So again, we have this hierarchy, and this is the strong coupling scale for gravitons, whatever that may be. I'm being as agnostic as possible, right? The whole way, and I'm trying to be as exhaustive of all possibilities as possible. What can we say about these scales? Well, again, in an EFT, as Paolo was remarking, this is sort of an uncalculable scale, right? In ratio with the Planck scale, of course. This is also kind of uncalculable, but there's a way to estimate it to give some upper bound, for example, some worst case scenario. Like we can look at some physical quantity, which makes sense in perturbation theory, in perturbative gravity, the setting that Luca was teaching us about, where we can estimate like some worst case scenario where for sure gravitons become strongly coupled by then, right? It turns out it's not the Planck scale. It may be, but it may not be. Of course, if this is the Planck scale, then everything is Planckian. So what can we look at? Again, let's assume that gravitons are weakly coupled. What can we compute? Let's say graviton propagator, right? So we can probe this scale with the graviton propagator. Now, why am I remarking that gravitons are weakly coupled? Well, sure, because I'm talking about this, but also because I want to remark that propagators in field theory are, honest to God observable quantities, but in gravity they're not, right? Propagators are not diff invariant; they're not gauge invariant quantities. In general, local quantities, local operators are not gauge invariant in gravity, right? They are not observables. Makes no sense. Now, you may ask, then why are you considering a propagator? It's a bilocal, quantity. Well, but as Luca excellently explained, I might say, you can gauge fix diffeos in perturbation theory. So this makes sense in perturbation theory because perturbatively, which means for small perturbations around your background of space-time geometry, gauge fixing works. You can do gauge fixing like Lucas showed, or more, sophisticatedly with the BRST and or Batalin-Vilkovisky frameworks. Non-perturbatively, you can't. It's impossible. There is no gauge fixing in gravity, nor in non-abelian gauge theory, actually. Which means that everything I'm saying cannot possibly work in outside of perturbation theory. Right? So it only makes sense in here, but luckily we are in this context, so it works. So we work with some gauge fixed thingy, right? And what did we have, after Luca explained it? We have some schematic description like this. We have some projectors, right? That's great. This is sort of the three-level schematic structure. But we are interested, this is the three-level guy. Then we have the one loop guy. So we can put some loop here. Now, what kind of loops can we have? Everything, because gravity couples to everything. So everything is here. Everything. So this is the one loop guy. Now, what is this contribution? Well, if you compute it, it turns out it's something like contains some order 1 constants. Then it contains your p squared over m Planck squared. This you could expect. This is the quantum coupling of gravitons, right? It has to show up. Actually, sorry, this is true in 4 dimensions. In general, I think it's d minus 2. And then there could be some subleading terms like logarithms, the classic logs that you get at one loop, whatever. We don't care about those. And then further corrections outside of the one loop piece we care about. Right? Why is this helpful? Because you see, this is the 3-level thing, and this is the one loop thing. So how far can we trust this? Well, when this becomes order 1, right? So this means can trust up to some scale. Now, from what I wrote, it looks like when p is over the Planck, right? Which is just this. We're saying that gravitons become weakly coupled by the time you reach Planck. That's blatantly obvious. But there's something I was hiding here. You see, because gravity couples to everything, and one loop effects are sort of Gaussian integrals of fluctuations for those who are familiar. This means that this thing contains sort of a trace over the one particle spectrum of the free theory around the background, right? This is fancy talk to say that there is a sum of basically the number of species of quantum fields that you have, or the sum of distinct types of fields with masses below whatever scale it is. So let me call this scale lambda SP. SP stands for species, right? Species meaning the different distinct types of fields that we have. Electrons, quarks, for example. And let's say that we can trust this up to this. This is the scale at which these guys become equal. So if you plug it in here, we get this. I mean, the more precise thing would be to say p squared and then divide by 2, right? You could do something like this. Right, let's say that this is the scale, but this scale also shows up here, right? It's a self-consistent thing. You can only sum up to the thing that makes the thing valid, right? So we are defining the scale by the fact that if you include this factor, you sum over all species up to the scale, this thing becomes over there 1. So if you put lambda sp in here and you solve the equation, what you get is the Planck scale divided by the number of, let me call this number n of lambda species. And you can also compute it using the density of states, right? You can use the density of states from whatever gap you have to lambda species, right? And so if you solve this d-2 thing, you get this. So this is an implicit equation, right? So it's kind of a fixed point of this process of integrating in species until you get to the self-consistent bound. And we can do this explicitly in many cases, right? Now, the simplest thing is when, you just have a bunch of, for example, let's say you only have your, let's say this is the UV cutoff. You have only your low-lying degrees of freedom, for example, the standard model, right? And let's say you have around, I don't know, something like 100 species. If you count all polarizations as distinct, you get something like 100, I guess. Then this number will be at least this. So yeah, would you agree? Like this is the number of low energy species. Then there could be something more. Other new species. Okay, and these, of course, this will be the lambda stuff, right? The scale of new physics of any kind, because these are new particles that we haven't seen, if any. And this is the scale of actual gravitational physics, new physics. So the worst case scenario is parametrically that you get something like the number of low energy species. And again, in the standard model, I think this gives you sort of a factor 10. So not a big deal, but it's not nothing either. So my point is that there is a scale which can be much smaller than Planck if you have a bunch of other light things relative to the Planck scale. And in string theory, this happens, right? Because in string theory, this is, you get a bunch of new things at the string scale. And, you can also have them here, of course. The strings are here, right? So you can have a bunch of things all the way up to this strong coupling scale, and then you get here. So what I'm saying is that in string theory, this is happen like the scale. If you solve this equation, you get a scale which is much lower than Planck. So the reason why I'm telling you this is that we can put a new thing here. We can put this lambda sp, and then we can put something we can actually compute. Like this, we can compute with some knowledge of the UV. Like we need to know what the new stuff is, something about it, the density of states. This, we don't even need to know that. We just can compute with EFT, right? And if our EFT has a lot of species, then the scale will be much lower. So we can call this lambda species IR, I don't know, and then you get Planck. So this is a useful way if you have like some hints about your review completion, or even if you don't, but you gotta be lucky that the number of species is big. You can really push the bounds on what these scales are much lower than Planck. Right? This can be useful at times. In string theory, again, this happens pretty much all the time that we can actually do calculations. Okay? All right. So was I supposed to do a break? Yeah. What? Well, let's say question time. Yeah. So this is a worst case scenario, right? So yeah, you can say it because it's an upper bound. Like it could be that the actual strong coupling scale is smaller than that. This is just an upper bound. The reason it's an upper bound is that not only we did a conservative estimate like that, but also that just because one quantity goes bad doesn't mean that it's the first to go bad. There could be some other quantities whose loop effects become important before the scale. And in fact, again, using the actual machinery of string perturbation theory, we can estimate this scale in some cases. Turns out it is much less than this. So there is an actual parametric hierarchy between all of these in string theory. That's you can solve this equation if you know the whole spectrum.
Yeah, 'cause you have a-
Yes, like you need to know something about the UV to estimate this. Yeah. Whereas this one, you don't. Okie dokie. So now let me speed up a little bit maybe on this last part. Good. So what are other things we can say about the EFT? So other things we can say about the EFT are two things that are very characteristic of gravity in various aspects, namely black holes and the S matrix. Now you could tell me, hey, wait a minute, the DS matrix has nothing to do with gravity, blah, blah. But there's something special about it in gravity. I'm gonna get to it. So what about black holes? Well, black holes are definitely something gravitational, and they have special features, right? So they have special features that tell us that something about field theory, or at least effective field theory, goes very wrong. And the reason is the following. You may recall that if you have a very massive black hole, it must be also very big in size. The horizon must be big, right? Because you get something like in 4 dimensions you get this, right? Mass is proportional to radius. In D dimensions you get this. So you get something like m Planck to the d minus 2. D minus 2, right? This has dimensions of mass. So you see, it's important that D be at least 4. Again, this means that heavy black holes are huge. Now you can just brush it off. Yeah, we know we knew that. But in the context of quantum gravity, it's extremely important because you see, if it is indeed true that if you smash particles really hard, you get some black hole. If this is true, if you smash them super hard, the resulting black hole will have a huge mass. But a huge mass black hole is also huge in size, which means that the curvature, let me call it like this, curvature. The typical curvature scale of the horizon is like R black hole to the minus 2. So if the black hole is huge, the curvature scales that play in the EFT of some observer outside are tiny. So this is what I'm going to call a tame regime. So when space-time is weakly curved, the one that we see, right? I'm calling it tame. So huge black holes are tame. But you see, so you scatter stuff super hard, a very UV regime, and you get back something that lives in the IR very well within the IR. And this is like arbitrarily so. Like the harder you scatter, the tamer the result would be. So if this is true, it's kind of weird, right? This is a mixing between UVA and IR physics, which in non-gravitational QFT never happens. And now you could say, yes.
And assuming that they produce black holes, so is it possible that they produce a bunch of mini black holes such that the mass is the same, so energetically should work?
I understand the question. Yeah, so the answer is it is possible, but it's very, 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 very unlikely. The reason being that, and this is what I was gonna say next, that black holes have an entropy, right? So they have entropy. And for huge black holes, there is an asymptotic expansion by Bekenstein and Hawking. So let's say the radius is much larger than the Planck length, right? For example, in this regime, you get the area of the horizon over 4g Newton. And just to be super safe, g Newton, like 8 pi g is m Planck to the 2 minus d, right? So we're clear. So you get this plus corrections. And so because of this entropy, it means that it is overwhelmingly more likely that you produce just a huge black hole because it will have a much bigger entropy than the sum of the little guys. Does that make sense?
The little guy will have like a smaller areas, obviously, but the bunch of them. I saw that one.
Yes, but I think so. Remember, the black hole version of the second law of thermodynamics, right? Like when black holes, like black hole processes can only increase the entropy, therefore the area when they're big, right? So it can only increase if you do this. I think this is true. Yeah. Okay. Of course, in this regime. Right? But then again, if it's not in this regime, the entropies are of order 1. So if you sum a bunch of order 1, like you gotta get to this. Good. So now you could say, oh no, I don't believe you. I mean, this may not happen. Could be. But what must happen anyway, because of this, is that these can be virtual black holes. They can be intermediate states because they're entropy. Therefore, they are mixed states, which have microstates, which are bona fide quantum states. Therefore, they appear as intermediate states because gravity couples to everything, right? So something like this can happen. And this amplitude will be dominated by these guys. So you will see this UVIR mixing effect, regardless of whether black holes are created physically by smashing stuff, microscopic stuff, even just as intermediate states, they will dominantly contribute in this way. Anyway, I digress. So this is one reason why, right? And moreover, the fact that the entropy scales like the area. Now I'm gonna say a word that maybe it's sort of um, dang, I was looking for a clever joke. The word is holography. So this formula plus all these considerations points to holography. And holography is something that in field theory cannot happen, right? Just structurally. And what is holography? Is the idea that it's partially motivated by the fact that an area law means that the degrees of freedom are not in the bulk of space-time, but on the boundary, right? And recall that the boundary was the only part of space-time which is super selected, the one that doesn't fluctuate, that you don't sum over in the path integral, which means that it's the only thing that you can use to define states, boundary conditions, and observables, right? Recall, there are no local observables. You can try to define relational observables, but the only way to do it is to have to integrate over all space-time. And once more, you are led to boundary conditions at infinity. You cannot just say, oh, I put a little probe here, and this is my boundary condition. You can't do that. There are no probes in gravity. Everything interacts with gravity. You cannot decouple things and make them probes, like in QFT, because if you make them heavy enough to decouple, they recouple because they become black holes. So this is very cool concepts, but there is more to why holography is suggestive. For example, not only black holes have this behavior, but also the canonical Hamiltonian of the ADM formalism has this behavior, because obviously it must be trivial in the bulk because it generates a constraint, right? Deep invariance, right? Whereas if you have a boundary, it will have support on the boundary. So dynamics is also sort of lives on the boundary, at least this is an indication. And another indication is that the observables also have the same fate. So this is why I was mentioning the S matrix, because there are no local observables, and relational observables are secretly boundary observables. The S matrix is the boundary observables, the boundary observable, right? So in gravity, at the exact level, you can only look at this action. S matrix in a broad sense, you don't have to scatter tiny little particles. You can scatter whatever states you want, right? So this is the case in asymptotically flat spacetimes. But if you are asymptotically anti-de Sitter, for example, there is an analog of the S matrix. It's called boundary correlators. And finally, that's it. There is no asymptotically de Sitter. That doesn't exist. So any sort of de Sitter-like situation, like the one we observe, should be like an unstable blob that decays to a bigger space-time. And this can happen in asymptotically flat space, not in asymptotically anti-de Sitter. So we are led to consider the S matrix as an observable in a weakly coupled theory of gravity, right? So this is the black hole part. And what about the S matrix? Well, you can consider some, let's say we look at the scattering of some gravitons, right? Let's say 2 to 2 for simplicity, right? What can we learn about this? Let's say there is an amplitude, right? An amplitude for this process. Now we learned from Anna's lectures that in GR at 3 level, let's say 3 level, this is what? Well, there is some kinematic factor which contains polarizations and momenta, right? Then this thing must have dimension 8 because there are 4 polarizations, therefore 8. Well, therefore 8 momenta because there are 8 indices here. Right? 8 momenta mass 8. Then there is a factor of G Newton because it's a 3-level amplitude. Therefore, whatever is here in the Mandelstam STU must have dimension 6 in the denominator. Right? And there must be simple poles and must be crossing symmetric. The only option is STU. Right, I just computed 3-level gravitons scattering. Yes. What? Yeah, but no. My point is, so the amplitude must be multilinear in the polarizations, right? And the point is that all terms must have the same dimensions, and there will be terms of this type. Therefore, if you have those terms, they will be compensated by some S powers of STU. And there are those terms, yes. Okay, I'm just normalizing things in such a way that the kinematic factor has, the simplest piece is epsilon, 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 p, 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 p. Okay. Right. So this is the GR amplitude. Now, can we say something about the UV completion? So in general, it's kind of a hopeless task, right? So we need at least one of two things. Either some huge amount of symmetry or redundancy, like a lot of supersymmetry, for example. Right? And there's people who are studying this, and I will mention some results about this later. But the most powerful crutch is the weak coupling limit. This means that we can consider an amplitude like this as a 3-level amplitude, right? Because there is a non-vanishing 3-level amplitude already, so it cannot be that it vanishes, right? So the question is, how can we describe this? And it will have the similar structure. Maybe this will receive corrections, but we don't care about it. There will be some correction factor, some FSTU, where more precisely, you divide these by the UV cutoff, right? So this is the structure of the amplitude. It must have the structure, right? And people tried applying bootstrap techniques to this kind of structure, the kind that Anna was mentioning, and they found very interesting things. They found, for example, that again, if graviton scattering is weakly coupled, there should be in the spectrum of species like this one, there should be like a tower of like higher spin states, which kind of looks very much like the string spectrum, right? Otherwise, the amplitude is afflicted by causality issues. You can compute like some time advances with the amplitudes, and also like the actual masses of these towers of species should start at the UV cutoff. And moreover, they very much look like the spectrum, like the spacings of the masses look like string spectra. So it kind of looks stringy, right? And then, very briefly, another thing you can do in this kind of vein by using the weak coupling limit, you can consider black holes, and you can consider the smallest black holes you can have in the EFT. So not when the size is Planck, but when the size is lambda UV to the -1. These black holes are still huge because of weak coupling, right? The length is still much bigger than Planck. So this formula still tells you that the mass is very big relative to the cutoff. So you can make black holes that are cutoff size and they are still fine in this limit. This is the galaxy brain move. And you can study the thermodynamics of these black holes using these kinds of things. And you can compare it with the thermodynamics of the new species, because they must be light because of this cutoff. And if you do that, they kind of have to match, because the microstates correspond to these species in some way. They have to match. Turns out these new states cannot be whatever you want. In order to match, they really must be of a very specific type in terms of the density of states. And we find that either the density of states is the one of like a QFT in higher dimension, so you're just moving the problem, or it looks like the density of states of a string spectrum. So again, we are sort of bootstrapping our way to strings from the weak coupling limit of gravity. This is what I wanted to say, really. So where are we at in time? 10 minutes. Okay, very cool. Any questions about this? No. Okay, good. So this was more or less my motivation to get to strings from scratch, from what we know about semi-classical gravity and effective field theory. Now, I want to tell you some things about strings. So like perhaps some misconceptions that are widespread, or what it does, what it doesn't do, and what it should do. Like what should a theory of gravity do? So maybe I can erase this while, if people have questions, they can ask. On Zoom, it's still fine. Okay. I think we're pretty much on schedule, because now we're gonna end this hour and a half, and then in the next part I will actually build the theory. So I said a lot of word, but I promise there's gonna be strings in the second half. All right. So now I hope I answered the question, why strings? Now I'll answer the question, what strings? Like what is the theory? What does it do? What strings do and don't, and what they should. So what do we expect a theory of gravity, quantum theory of gravity, to do in the first place? Well, we want such a theory to be complete. All physical regimes should be calculable or predicted, or whatever you want to call it, at least in principle, right? Maybe we are not good enough at doing calculations, but the theory should be well defined in some way. So what they should do, so what any theory should do, predict in principle. Maybe it's hard to compute, but whatever. Predict both the UV and the IR physics and everything in between. Now we expect, as I said before, the UV to be universal in the sense that it washes out the IR behavior, and then eventually it collapses back into the extreme IR via black hole formation, right? So in this sense, universal. And the IR, well, it can be messy. But calculable, right? can be messy because you can have multiple vacua. Now, I want to emphasize this is not a thing about string theory. It's a thing about any theory of gravity, because even the standard model, the Grismeft, has this property, right? The standard model, effective field theory coupled to gravity, has a lot of vacua, right? You just need to compactify. You just need to go to 3 dimensions, 2 dimensions, 1 dimension. You have a lot of vacua. Similarly, in the highest possible dimensions, string theory has like a handful of vacua. Perhaps even 1 in the highest possible dimension, similarly to the standard model up to the Higgs mechanism. So it's not surprising, right? And then if you reduce dimensions, doesn't need to mean that there are extra dimensions. I will come to that. If you are in lower dimensions, whatever that means, it's normal that there are multiple vacua. It's completely expected. It happens in the standard model, right? So it's just a matter of the fact that not that the dimension be 4 or higher, but that the maximal dimension be 4 or higher, right? That's the difference between, say, the standard model effective field theory and what happens in string theory. It just so happens that the highest possible dimension for a nice, tame, weakly curved spacetime is bigger than 4. It's a fact of the theory. But it's the maximal possible. Doesn't mean that it tells us absolutely nothing about what it should be. It's just that it's the simplest case. Again, identically to the standard model. There's no difference, except instead of 4, you have like 10 or 11, but we will see that. Okay. So, okay, cool. So this is what you should do. And indeed, we will see exactly how this works. Then the theory may be even more generous than that, because there could be a messy infrared with lots of vacua, lots of different types of low energy physics, but there could also be some general properties. General properties. This is a bonus, right? Like no theory, the doctor didn't order this, right? So string theory happens to give us that. And there are, general arguments, generic broadly quantum gravitational arguments that there should be these general properties, and they happen to hold in string theory. We will review some of them tomorrow. So this is sort of a bonus, right? It didn't have to be so generous, but I mean, these general properties, of course, have a price to pay to be so general, and yet low energy stuff that we could see, right? The price to pay is that they tend to be not very sharp. They tend to be like inequalities, like this mass should be smaller than this other thing, right? And it happens that the standard model satisfies all of these, all the known ones, but by a lot. Like there's a lot of margin. So the inequalities are shallow in some sense, at least as far as we understand. They can be sharp inequalities, but there's a lot of room for our universe to satisfy them. So it's not very constraining in this sense. So this is the price to pay to have something general to say at low energies. But we also have something to say at high energies. We can tell our experimental friends since the 80s what happens if you smash particles super freaking hard. So this we can say with a fair confidence. Okay, so what does it do? Well, it does exactly what I just said. Plus, so what it does this with no free parameters. So the theory has no free parameters. Obviously, a parameter is a dimensionless quantity. Otherwise, it's just a scale that says the units, right? And no global symmetries. No global symmetries. Again, this is one of these kinds of properties that we'll see. So it does this in this way. Then it also has some curious other little quirks. For example, if we want our space-time to be nice and tame and without, tachyons and wild stuff like that, it must contain fermions. This was actually, to my knowledge, proven last year. So it's kind of, I get you there. I mean, it was more or less known before, like since decades ago, but to my knowledge, it wasn't actually shown in this regime. So there must be fermions. Then there is a constraint, as I said before, on how many dimensions you can have. And you can have, again, we are putting our lower bound at 4 for gravitational reasons and Fino reasons, but this is a theory lecture. And the upper bound, again, with this condition that the universe be stable, is 10 if we want weak coupling, or 11 if we don't, right? So if there are extra, again, there need not be all of these. It could just be that we have 4D and that's it. There need not be extra dimensions. I will go more in depth into this later. I mean, maybe there is a need and we just don't know it. We haven't proven this, at least again to my knowledge. But the upper bound for a nice stable spacetime is this. At weak coupling is a bit lower. But the point is, if we see 15 extra dimensions or total dimensions, the theory is wrong. Right. So this is a good bound. Okay. What else? All right. Supersymmetry. So in the last 10 seconds, I'm gonna tell you what it doesn't do. What it doesn't do. So again, I told you some things it doesn't do, like it doesn't predict a single vacuum. But again, it's not surprising. The standard model has the same feature. We need an extra input from the standard model to know that we live in 4D, for example, 4 extended dimensions, to fix the vacuum after Higgsing. So again, it's not surprising at all, but still it doesn't do it. Another thing it doesn't do, it doesn't tell you whether supersymmetry is there or not. So basically, supersymmetry in space-time, it could be there, it could not be there, it could be there, but it's broken. We don't know at any scale. Like, it doesn't fix anything about it. The only thing is that there are vacua with SUSY, there are perturbative vacua without SUSY, there are vacua where SUSY is there, but it's broken. High scales, low scales. The only thing that SUSY actually does for us is it guarantees full, complete, exact stability, not just perturbative stability. And it makes our lives easier for calculating things. Not very surprising. Rotational invariance does the same. So this is the status of SUSY there. I will come back to it. And with this, I think I should close. Thank you. Feel free to. Yes. What? Any questions? Yeah.
Why of the number of extra dimension corresponds to the degeneracy of the vacuum state. So how we do not run into problems when we reduce the number of dimensions from the string theory perspective, like with ghosts or stuff like that.
Right. Very good question. So the degeneracy aspect, the idea, very broadly speaking, is you have a maximal dimension. Okay. Let's say the vacuum is unique in there. Okay. Or at least you have like a bunch, like a 5 or whatever. You reduce. Okay. What does reducing mean? Well, in classical or semi-classical gravity in EFT, reducing dimensions means that the rest is like extra dimensions that are small and compact. Right? So in string theory, you can have that. You can compactify, we say. Or you can fill in where the extra dimensions should be. You have other kinds of degrees of freedom instead. So what happens is that there must be other degrees of freedom. We will see that very explicitly. And again, to my knowledge, it's not proven in any way that they must be extra dimensions, and I will comment on this more explicitly. But the point is, if you reduce, you have some freedom in how to choose these degrees of freedom, or even if you do only compactifications, so actual extra dimensions, you still have some choice in how they look. Now, the reason why this doesn't lead to pathologies or instabilities is that yes, you can choose somewhat what these extra dimensions, for example, look like. But you cannot choose willy-nilly. You cannot choose whatever you want. There are constraints, very strong constraints. And I will give a very sharp definition of what these constraints are in weakly coupled string theory. And these constraints ensure at least that perturbatively everything is fine. In some cases, you can even prove that non-perturbatively everything is fine, so that there are no issues. Like the observables in string, like the S matrix in asymptotically flat sectors is unitary, causal, everything is fine. It satisfies the basic principles of physics. In fact, the bootstrap kind of tells us that if you impose those, you kind of have to go string at some point. So yeah, there are no pathologies, even if you have some freedom. Yeah. So if we're running late, maybe we can just. I mean, I'm happy to answer questions at the coffee break, of course. No?